Okay, we've got a man in a boat right here in the water. That's this blue area right down in here. He's 3 miles off, closest point to shore. He has to get to point Q as quickly as possible. And that point is 3 miles down the coastline and 2 miles inland. First of all, if you notice these two right triangles, this is a hypotenuse for the red triangle. And we're assuming he's rowing to some point x between 0 and 3. 0 and 3, right down here. So if this distance is x, this distance is 3 minus x. Okay, and by the Pythagorean theorem, this red hypotenuse is the square root of x squared plus 9. And this green hypotenuse is this leg squared plus this leg squared, take the square root. Now for the time function, these represent distances. We have to divide by the rate to get the time that he's traveling along those paths. So the total time function is this distance divided by 2 because he rows at 2 miles an hour. He's trying to get to the shore rowing, plus the distance that he walks is divided by 4 will give him the time that he walks. Okay. And right now this is showing, for an example, the time that it takes him if he rows 0.72 miles down the coast to a point 0.72 miles down the coastline. Turns out this black graph right here is the graph of this function, and you can see it reaches a minimum at about 1.1 miles. And there's the total time that it takes him. This expression right here is what you get if you set the first derivative of t equal to 0. And I haven't got all the work for that on the next board. It's not pleasant. But at this point, you have to use some numerical method to find the value of x that produces a value of 0. And this is showing Newton's method. It looks like on the fourth iteration, we start repeating at several decimal places. So 1.1 miles down the shore looks like it produces the minimum amount of time. If I share my screen and actually go to this site, if I move this point towards that 1.1, there's 1.1 right there, 2.28. But any other time, you'll see it's greater than 2.28. And if I move to the endpoints, 2.6 minutes there, or let's see, we're doing miles per hour. I guess that's in hours, and 2.4 there. So there's definitely a point on the shore that he can row towards to get him as a minimum time. Here's the work involved in finding the first derivative and setting it equal to 0. Here's t prime. Use the power rule. 1/2 times 1/2 is 1/4. Reduce the exponent by 1 and multiply by the derivative of the inside, chain rule. Same thing over here. 1/2 times 1/4 is 1/8. Reduce the exponent by 1, multiply by the derivative of the inside. Here we've got to use the power rule. 2 times 3 minus x, reduce the exponent by 1, multiply by the derivative of its inside, -1. Okay. And if you simplify all that, you get this. Now the question is, if you set that equal to 0, what's the best way to solve that? Well, there's a whole bunch of different ways. My suggestion is maybe to get the radicals so they're on the same side and part of a fraction. These cancel. Now, if you square both sides, that will eliminate the radicals. And this is what you get. By the way, this 4 comes from that 2 squared. And after you've squared both sides, then you've got to cross multiply, combine similar terms, set it equal to 0, and solve that equation for x. And then you probably have to apply the first derivative test to make sure that this is going to generate a minimum. Okay, so I'm assuming to the left of 1.1, t prime is negative, so the original function is decreasing. To the right of 1.1, like a 2, t prime is positive, so increasing. So we got a minimum at 1.1. And then you would test the endpoints. If he doesn't leave the shore at all, or if he rose directly from this point out to there and then up to there, those might generate absolute mins or maxes, but they're not as small as if he rose to this 1.1 distance. Okay, there you go. Hope that helped. If you have any questions, post a comment.